Okay. Anyway, so we left off. Ooh, good shot. We left off yesterday talking about this particular situation where we had a bowling ball, and the bowling ball had a mass of 6 kilograms, a velocity of 10. So how much momentum does it have? 60. We roll the ball with 60 kilogram meter per second of momentum. It strikes a pin. The pin is motionless, so it starts with 0, but then the 1 kilogram pin moves backwards at 20 meters per second. How much momentum did the pin take from the ball? 20. Okay. So again, the pin had to get momentum somewhere, so it got it from the ball. So the 1 kilogram pin moved backwards at 20 meters per second, so it took 20 kilogram meter per second from the ball, leaving the ball with how much? 40. Then we realized that if it has 40 kilogram meter per second left, we just divide by the mass of the ball, 6, and we get about 6.6 meters per second for the resulting velocity of the ball. Make sense? Yep. Okay. So I have some other things that are kind of fun. You might have seen this before. So just like that, I got a basketball, and I got a super ball, and then you've seen this before, right? Where you take the ball, and you drop it. And the dust comes down. Uno, stand over here. This is a fun thing. If you have a basketball and a gerbil, you can do this. Flying? Yeah. Or a guinea pig. Probably. Golf balls work too.
Oh, I have a lot of those. Oh my God. I'm so doing that thing at home. Thank you. I tried to do it with the golf ball.
There's always a risk of damage when you're doing science. And then, let me see if I can bounce one to somebody. I'm going to bounce it off the desk, and I'm going to get it right to Julia. Yeah, like beer pong. Here, we'll try this one. Ready?
Science.
DJ by your left foot.
We'll try it again. You ready? Here. This one's going right to you. Okay. And the other one? Oh. It's really hard to catch it when there's like light right there and you're all dark. Okay, we'll try this one again. Ready? What's wrong with that ball? Yeah, they're both rubber. These are kind of fun. They're called happy sad balls, and they're both. This one's happy. This one's sad. It's because of how the materials are cooled. The molecules don't act like springs like they should. The molecules kind of slide past each other. So if you have materials where the molecules are really close together and they act like little springs, one pushes on the next, then you get things like a super ball, or a happy ball, or a golf ball. But then when you get materials where the molecules aren't allowed to touch each other or slide past each other, then you get molecules like Nerf, or the sad ball, where the molecules aren't pushing against each other, they're sliding past each other, so the energy isn't exchanged. Or a good example, foam. There's too much space between the molecules. So that's kind of fun. I just thought you might enjoy that. I have all sorts of fun little toys all over the place. Okay, so moving on. Any questions before I move on? Okay, so today we're going to focus on inelastic collisions. And an inelastic collision occurs when there's a loss of energy. Most of the inelastic collisions that we're going to focus on in this class have to do when two objects become one, stick together, or one object breaks apart. Okay? So an inelastic collision that we're going to be working with is when objects lose energy in some fashion. Sometimes the attacker and the target become a single mass. Most of the inelastic collisions, like I said, will have to do with two objects becoming one, or one object breaking into pieces. If you like math formulas, here's some math formula for you. BF final equals the momentum of 1 plus the momentum of 2 divided by the mass total. And the momentum of 1, 2 is just the momentum of 1 plus the momentum of 2. We're still going to use the chart, though. I'm still going to walk you through the chart if you're not the kind of person like me who doesn't like a lot of formulas, like to actually just work it through step by step. So a diagram of an inelastic collision would look like this. M1, which is moving, strikes M2, which is motionless, and then M1 and M2 move together. Like this. This is our M2, which is motionless. Here comes our M1, and they move together. Where all of the momentum from the attacking car has to distribute itself over the mass of two cars. So it slows down. Inelastic collision. So that's one type of inelastic collision. The other type of inelastic collision goes like this, where you have one object, which becomes two objects. Okay. You have one object that has how much momentum? How much momentum does the system have right now? Okay. The total momentum of the two-car system is a big fat 0. Okay. Now I'm going to hit the thing. After they exploded, what was the total momentum of the big fat system? It was still a big fat 0. What? But they're moving. I know they're moving. Okay. What's the momentum now? 0. What's the momentum now? 0. Because this guy's momentum should exactly balance this guy's momentum. Does that make sense? So if they're 0, before they hit, maybe this one is plus 10, maybe this one's minus 10. Get the idea? Okay. So those are the two kinds of inelastic collisions that we're going to deal with, where two objects come together or one object breaks apart. Okay. Remember that animation? Upgrades. All you need is a guinea pig and an exercise ball. Both of which can be bought at Walmart. Okay, so in an inelastic collision, objects collide, come together, or break apart. Just a quick reminder that when you have an elastic collision of different masses, that you need to realize certain things happen. If you have the same mass in an elastic collision, and in an elastic collision, the first mass will come to a stop and transfer all of its momentum to the second mass. We don't do two-dimensional collisions in this class. If you take physics AP, or you go on to take more advanced physics later on, then you will have to do two-dimensional collisions. It's really not that hard. It's just vector. Remember how we resolved vectors and their components back in October? It's exactly the same thing. It's just instead of resolving velocity vectors or force vectors, you're resolving momentum vectors. We're not going to do it in this class because, quite frankly, you already know how to do it. I'm not going to bother taking the time. Okay? So if you understand momentum vectors, then you're going to be fine. So that's how a two-dimensional momentum vector works. You resolve both the x and the y. So the ball's coming in with only x, and then this one's going up with y, and this one's going down with y. How does the y momentum of the green ball compare to the y momentum of the blue ball? Yeah, they're the same. They have to cancel out. The green ball comes in with no y momentum, so it has to go out with no y momentum. Does that idea make sense? Good. We're going to do that. Okay. So, and then different masses. Remember what happens when a large mass strikes a small mass? What does a large mass do? Yeah, it chases it down. Okay. So if a large mass strikes a small mass, it chases it down. If a small mass strikes a large mass, it recoils. So in an elastic collision, when a small mass strikes a big mass, the small mass recoils. When a large mass strikes a small mass, the small mass moves on, and the big mass chases it. Okay. Consider this. I had a basketball around here, but not anymore. Okay, so consider this. Tennis ball, represented by an orange ball, or an orange Nerf ball, travels away from you at 4 meters per second, hits the board, and returns towards you at 3 meters per second. Lean over to your neighbor and mention to him or her what the change in momentum is. What is the change in momentum? The ball is moving away from you at 4, hits the board, and comes back at you at 3. Oh, sorry, change, yeah. We're going to assume the ball is just 1. Sorry. Just 1. 1 kilogram. Yeah. So, who says the change in momentum and the change in velocity is 1? Okay. Who says the change in velocity and the change in momentum is 7? It is 7. It is 7. Because remember, we're talking about vectors. So if something's moving away from you at +4, then coming back at you at +3, there is a change of 7. Does that make sense? No. Okay. Momentums are vectors. So if the 1 kilogram ball is traveling to the right with a velocity of 4, it has a momentum of +4. Because we have to have a plus or minus coordinate. So we're going to take to the right to be positive, to the left to be negative. If it bounces off the board and comes back at 3 meters per second, that 3 is not 3, but it is -3. So the difference between -3 and 4 is 7. Okay? Quick reminder, if a ball travels down with a downward momentum and then travels up with an upward momentum, is momentum conserved? No. What do you have to have momentum be conserved? Impulse. You have to have impulse. Momentum, impulse, momentum, impulse, momentum, impulse. So as long as you are moving, you have momentum. But since momentum is a vector, a downward momentum cannot become an upward momentum unless you have an impulse in between. Does that idea make sense? It's one of those weird ideas that almost everybody, even physics teachers, forget. Okay, so downward vector, upward vector, those two things can't be conserved unless you have an impulse happening in between. Let's do an example. Here's a fun little animation. So here, a car with a mass of 1,000 and a motion of 20 strikes a truck with a mass of 3,000 and a velocity of 0 initially. So all the momentum is coming from what object? The car. The car has a mass of 1,000, a velocity of 20, so it has a momentum of 20,000. And since the only thing moving is the car, the total system has a momentum of 20,000. When the car sticks to the truck, the system still has 20,000 units of momentum, but now that momentum has to be distributed over 4,000 kilograms. So the two move together with a final velocity of 5 meters per second. Let's just stare at that for a little bit before we do an example. Stick. Stick. Okay. Questions before we do an example? I gave you that formula to play with. I don't like to do formulas. I like to do charts. I like to do the M1, V1, P1 chart. So here we go. Consider this scenario, and I realize the animation is going to look weird because I got it off Microsoft PowerPoint. Consider Jed. Jed's a 60-kilogram quarterback running at 8 meters per second, and he hits Buck, the 95-kilogram linebacker running in the opposite direction at 10 meters per second. My question to you is this. The two collide and stick. What is the mass, velocity, and direction of the Jed-Buck system? So in starting this out, we want to do our chart again. M1, V1, P1, and M2, V2, P2. This will be Jed, and this will be Buck. So go ahead and start filling out the chart for Jed Buck. velocity of jet initially. Yeah, 8 meters per second. And what is the velocity of buck initially? If by 10 meters per second you meant negative 10 meters per second, you're exactly right. Remember, velocity is a vector. And if jet's moving forward, then buck has to be moving backward. If jet has a positive velocity, then buck must have a negative velocity. That's muy importante, as they say someplace. Yeah.
Can we make 10 positive and 8 negative?
We can, but I don't want to.
Alright, just curious.
Yeah, we totally could. We could basically say forward is negative, backward is, depending on whether or not we're rooting for their team. Okay. So what's the momentum that jet's carrying into the system? 480 kilogram meter per second. And what is the momentum? Is that not right?
No, that's right.
Okay. What is the momentum that buck is bringing into the system? Negative 950 kilogram meter per second. So the total momentum of the jet buck system is how much? How much? Yeah, negative 470 kilogram meter per second. Why is it negative? Because 480 plus 950 is negative. What is the mass of the jet buck system? 155 kilograms? And that gives us, or allows us to find, the velocity of the jet buck system. About 3? About 3.0?
How did you get that?
I realized that our formula, delta P equals m delta V, still holds here. So if I have the momentum of the overall system, I can divide by the mass of the system to get the velocity of the system.
So,
It's negative because buck traveling in the opposite direction has more momentum. So we add buck's momentum to jet's momentum. The resulting momentum is momentum of the entire system.
Why is it the velocity?
Like I said, negative 3.0 meters per second. Is that what you're going to say? Were you going to mention that too? Okay. Yes. Negative 3. Thank you. Okay. Give me a thumbs up if you're good so far. You understand this coming together thing. We're getting there? Okay. Can we take it from the top? All right. So we have two objects. One object moving from the left, going right, has a mass of 60 and a velocity of 8 for a momentum of positive 480. The other object going from the right to the left in the opposite direction has a mass of 95, a velocity of negative 10 for a momentum of negative 950. We add the negative 950 from buck to the 480 for jet, they stick together. But because one has more momentum than the other, they're going to move together. It's kind of like if I made these two things stick, but I made one go really fast and one go really slow. So the overall momentum divided by the overall mass gives us the velocity of the two things together. Moving on. Okay, this is kind of fun. You need to write this down, but it's actually kind of fun. You're going to write down what's right here. There's a thing you might get to play with called the Ballistic Pendulum. I don't have one here. One of these days I'm just going to build one for the AP Physics class. We have a reverse ballistic pendulum, but it'd be really fun to have a ballistic pendulum and come in like shoot BBs at it or something. It's basically, it's a box full of clay, and they shoot a bullet into it. And that bullet sticks in the clay, and then the whole box goes up. And the change in potential energy of the pendulum, they work backwards to find the change in kinetic energy, then find the velocity. Then they can find out how much energy the bullet was carrying, how much velocity it was carrying. Kind of neat. But what you should do is this. Consider this. This is a reverse inelastic collision. This is a situation where one object is becoming two. Imagine you took a crossbow and hung it from light strings. Hung it there. And then you went and hit the trigger. Not adding any momentum to it, hit the trigger. The bolt goes one way, and the crossbow goes the other way. Make sense so far? So this is a reverse inelastic collision where one thing breaks into two things. So you have a 225-gram crossbow bolt is fired at 75 meters per second. What is the initial reverse velocity of the 4.6 kilogram crossbow? It's a reverse inelastic collision. When you're doing a reverse inelastic collision, which as you are about to do, you take this and you put it up there. Take PT, MT, and VT and put it up there. And then do M1, V1, P1, M2, V2, P2. So give that a try. See if you can figure out how fast the crossbow is moving backwards when it fires its bolts. Solid particles that you can fall off. Did yours start the same way mine started? No. Okay. The mass of the crossbow plus the bolt is 4.6 plus 0.23, which is 4.83. So the mass of the crossbow bolt and the crossbow together before they are launched is 4.83. Additionally, they're just hanging there. There's no motion, so they have no momentum. Okay. Does that make sense? Why I wrote this up there? The velocity isn't moving yet. So basically what's happening is this. When in a normal elastic collision, two objects are coming together. This is a reverse inelastic collision where one object is breaking into two pieces. So it's like this. Crossbow, crossbow bolt. And then they break. Okay, does that make sense? But one's obviously way more massive than the other one. Yes? Yep, that's what we're doing next. Yeah. Okay, so then we realize that the mass of the bolt is 0.23 kilograms. It's traveling at 75 meters per second. How much momentum does the bolt have? Okay, I'm going to round this to 17 kilogram meter per second. So if the bolt has 17 kilogram meter per second of momentum, where did that momentum come from? Of the crossbow. So it had to come from the crossbow. So if the bolt got positive 16 kilogram meter per second, the crossbow had to get negative 17 kilogram meter per second. Did I say 16? I meant 17. And we know the mass of the crossbow to be 4.6 kilograms, and that gives us the velocity of the crossbow, which should be about what? Yeah, about negative 3.7 meters per second. Okay. In other words, the crossbow gave momentum to the bolt. Whatever momentum the bolt gained, the crossbow had to gain as well. Okay. They both started with 0. But one object went that way with leftmost momentum, one object went that way with rightmost momentum. Whatever momentum the left object got, the right object had to get as well. That's a reverse inelastic collision, where something explodes. Give me a thumbs up if you're with me so far. Okay. Now, one more. This one doesn't even require writing stuff down. This one's one you can do in your head. Consider this. A 45 kilogram girl on a 4 kilogram skateboard is moving forward at 8 meters per second. She jumps off. How fast is the skateboard moving backwards after she leaps off at 9 meters per second? So you can go through the whole rigmarole if you want. But you can also realize that she increased her momentum. Question? Whatever change in momentum she had, that's the same change in momentum the skateboard has. So she increased her momentum by increasing her velocity. She goes from 8 meters per second to 9 meters per second. What's the change of her velocity? Not a trick question. 1. Yeah. And she has a mass of 45. So she increased her momentum by how much? 45. Which means the skateboard changed its momentum by negative 45. Yeah. So if she goes forward at 45, that means the skateboard's going to change its momentum by negative 45. Does that idea make sense? Okay. What's the mass of the skateboard? 4. What's 45 divided by 4, approximately? 11. So the skateboard changed its velocity by 11. If it was originally going forward at 8, now it's going backward at 3. Okay, see how that works? She gave herself more momentum, but by doing so, she had to change the momentum of the skateboard. She gave herself 45 units of momentum more, so the skateboard had to get 45 units of momentum backwards. 11 meters per second. 8 minus 11 is negative 3. Okay. This is the other type of reverse inelastic collision. Sometimes you have an object moving, like, let's see what kind of timing I have. So let's say these guys go moving, and then that happens. Not too bad, actually. Okay. So the objects were moving, and then there was an inelastic collision, and they did their thing. That's the other type of reverse inelastic collision you'll see. Questions? Okay, cool. This is just fun.